Okay, so we are going to talk about the output analysis in the last part of this lecture. When we run the simulation model of a system and we try only a single policy in that simulation model, then we need to estimate the output performance of that policy, of that decision that we are going to make. And that is going to be called the absolute performance of that policy. Now, let's just say we have two system designs or two different policies in the same system. And we need to choose between these two policies, which one is better in performance. Then we need to compare the results of the simulation model under these two different policies. And that is going to be a relative comparison in performance. So in that case, we call the output analysis a relative performance comparison. So here we are going to study the output analysis in two parts. In the first part, we are going to estimate the absolute performance of a single design. And then in the second part, we are going to estimate the relative performance of two different alternative system designs or two different policies, and we are going to compare them. So we are going to start from the simple. Let's just analyze the outputs for a system. We are going to give some preliminaries about the output analysis and explain what output analysis is. And we are going to talk about the absolute measures of performance. And we are going to talk about the point estimation, which is something you know from the statistics course again. And we are going to talk about the confidence intervals and prediction intervals, because these two are going to be essential in measuring the absolute performance of a system design. And then we are going to explain how we can analyze the output for terminating simulations and steady state simulations. But we need to understand the difference between a terminating and a steady state simulation for that. As a fourth part of this chapter, we are trying to develop confidence intervals for specified precision. Basically, in order to get accurate results about the outputs, how many replications should we run? So this is the question. How many replications I should run for getting desirable accuracy for the results? In order to get this accuracy, how many replications should I run is going to be obtained with confidence intervals with specified precision. So I say that if the half of the confidence interval is less than 1% of the value, then it is going to be reliable. So the relative error is going to be 1%, I say. Now, in order to make my confidence interval as narrow as this one, how many replications should I put? I am going to answer this question. Okay, so let's move forward. Let's talk about the output analysis. The output analysis is the examination of data generated by a simulation. Actually, the output analysis practically is performed by Arena, because Arena gives you a report with the output performance metrics, with the confidence intervals calculated already. So all you need to do is to make comments on that, okay, in Arena. So advanced simulation software will make the output analysis for you. But actually, we need to learn the theory of it as well, of the output analysis. Now, imagine you have a valid model now. You are sure that your model is valid. Now, you are going to make decisions based on the output performance metrics. For example, output analysis answers this question. What can we say about the average time spent in the system by entities? And the purpose of this output analysis is what? To predict the performance of a system. So, the absolute performance. Or, I'm going to compare alternative systems to decide which one is better. And that is the analysis of relative performance. Here we are just going to focus on the absolute performance. In discrete event system simulation, random number generators are used to generate the random values of input variables. So you know the input variables in this discrete event system simulation are generated by random variable generators. So they are generated by pseudo-random number generators, if you know. The simulation output exhibits a random variability under different sequences of random variables. So at each replication of your simulation, a different random number sequence is used. Based on the different random number sequence that is used, different outputs are obtained. So the output variables, they also possess some variability due to the randomness coming from the input values. Therefore, the output across replications requires statistical analysis. So when you run different replications of the same system with the same policy, but with different random number sequences, then the outputs are going to be different, but they are going to have some statistical distribution and they are going to have an average. And if we want to make a comment on the expected performance metrics, such as the average time spent in the system by entities, then we need to make a statistical analysis across the replications. Now, suppose the performance of a system is measured by theta. And let's just say this theta is the average time spent in the system by entities. The system time, basically. The average system time for all entities. And in most systems, it is impossible for us to know the exact value of theta, right? Either you are going to observe this system until the infinity, or you are going to run a valid simulation model again until infinity. So it is impossible in any way. I mean, for terminating simulations, it may be possible, but still there will be some errors coming from the statistical procedures and observations. Therefore, this theta cannot exactly be known, but we want to know it. Not exactly, but with a certain accuracy, we want to know it. So the result of the simulation will be theta hat, and it is going to be an estimator of theta. It is not going to be exactly equal to theta, but we will say that it is just a predictor of it. And the precision of this estimator can be measured by the standard error of theta. So when we calculate the standard error across replications for this performance metric, we can also talk about its precision. How accurate is that value? The standard error helps to provide a confidence interval for the real value of theta. So by calculating theta hat and the standard deviation coming across the replications, we can provide a confidence interval with a certain confidence level, such as 95%. And we can say that with 95% probability, the true theta, the true average time spent in the system is in this interval with 95% confidence level. But it may not be there as well. So how many replications are required to obtain a desired accuracy is the question. The final question that we are going to answer in the chapter is this. So how many replications should you run? If you run too many replications, then it is going to be more and more accurate, but is that necessary to wait that long time? So we need to determine what is the necessary amount of replications, because we do not want to wait so long to come up with the results. Now, there are two types of simulations with respect to the output analysis. The first type is a terminating simulation. In terminating simulations, the replications run for some duration time, TE, until a specified event E occurs. For example, imagine a supermarket and we want to run a simulation of the supermarket, but the supermarket closes at 10 p.m. It opens at 10 a.m. and it closes at 10 p.m. Let's just say from 10 a.m. to 10 p.m. So a single replication that belongs to a single day is going to be a terminating simulation because each replication ends with a certain event. What is that event? When the clock shows 10, that is the terminating event. And another terminating event can be what? After 10, when all customers leave the system. This can be another terminating event. And these are the examples of terminating simulations. A workday in a bank until closing time is a terminating simulation because the closing time determines the termination of the replication. A workday in a bank between 1 p.m. and 3 p.m. because we are given a time interval here, the simulation replication will start exactly at 1 p.m. and it will end exactly at 3 p.m. because after 3 p.m. we are not interested. The problem that we intend to solve is happening between 1 p.m. and 3 p.m. Let's just say. And a workday in a bank until all clients leave after closing time. Again, it's a terminating simulation because it requires a terminating condition to happen. It's a terminating simulation. It ends. A maintenance system until its first failure. It terminates when you observe your first failure. And a financial portfolio until it yields a certain rate of return. Again, when this financial portfolio gives you enough profit, satisfactory profit, you stop the simulation, you terminate it. Okay? And it is going to happen at some point of time. I mean, assuming that the financial portfolio is a clever portfolio that you have created. So both the initial conditions and the stopping time must be well defined in terminating simulations. Another type of the simulation is the steady state simulation, where we run the replications continuously over a very long period of time, and the termination time is still denoted by TE, that is sufficiently large. So originally, the system continues to work for a very, very long amount of time. However, even though you want to run a simulation of this non-terminating system, and you want to measure the performance metrics of the system over a very long period of time, for example, the average queue sizes or the average time spent in the system over a long period of time, you need to define an end for your replication, which can be a very long amount of time. There can be a final time for each replication, which can be very long, but this does not mean that this is a terminating simulation. This is a steady state simulation, because you want to observe the behavior of the system for a very long amount of time. So, for example, continuous production systems. Imagine an assembly line for casting operation. The casting operation is a very expensive operation if you build a serial production. In that case, these systems usually work for 7 days a week and 24 hours for a day. Or there are assembly lines which work for 3 shifts over 7 days over a week. These continuous production systems, they work for an infinitely long amount of time. So we are much more interested in the steady system behavior of such systems. Or operating computer networks. The computer networks are always working. For example, there is no time when you intend to send an email at 3 a.m. in the midnight, whoever you are sending it to, I do not really know, okay? Sometimes I get these kind of emails from students, at 1 a.m. about the exam tomorrow, interestingly. Yeah, so, computer networks work 24 hours a day, right? So these are systems which need to be run with a simulation model that is going to be observed for steady state analysis. They are not going to be terminating simulations, or communication systems like call centers, which work 24 hours a day. In these steady system simulations, the analysts are interested in the steady state properties of the system, which are not influenced by the initial conditions. So remember now, when you run a system, it always starts as empty. However, I am just interested in the long-term behavior of the system. So what happens when the system works for a large amount of time? So I want to remove the effects of the empty system in the beginning.